Next, we'll continue with lens combination. Yes, why are we combining lens? Why do we use more than one lens? It can be a convex or concave lens. We know that most of the optical instruments we use has more than one lens. That is a microscope, a telescope, a camera. Everything has more than one lens. So what is the advantage of using more than one lens? When we combine lenses, we get a combination of desired magnification. This is the first point. Second is we get an increased magnification. Third is the sharpness of the image can be increased. Fourth is the image that is formed by the first lens acts as an object for the second lens. So the final image can be made erect with respect to the object. This is the fourth one. And the last is we can minimize certain aberrations like spherical aberration, chromatic aberration than by using one lens. So if you combine more lenses, all these aberrations can be reduced. Aberrations means defects of the lenses. For example, if you have a concave lens, you have a number of rays that is incident on this lens. The lens which are close to the axis, this is the principal axis. The rays which are close to the axis are called as paraxial rays. And the rays which are away from the principal axis are called marginal rays. And these paraxial rays, they focus at one particular point, and these marginal rays, they get focused at some other point. So finally the image will be blurred. So this is what is called as spherical aberration. When we have chromatic aberration, chromatic itself means light. What happens when white light is incident on the lens? You can see that this blue light, suppose if this is blue light will be converged at one point and red light will be converged at some other point. Again the images will appear blurred. This is called as chromatic aberration. So the aberrations can be reduced to some extent when we use more than one lens. Now let us see the lens combination. Let us consider two thin convex lens. Let us consider two thin convex lens. Let us name it as A and B. Let the focal length of the first lens be f1 and the focal length of the second lens be f2. Here we have used two convex lenses, two thin convex lenses. Let us place the object on the principal axis. A ray of light incident on the first lens. Along this direction it is incident. After refraction, forms an image somewhere over here. Let me name it as I1. It gets refracted on the first lens and the image is formed at I1 in the absence of the second lens. Suppose if we imagine that the second lens is not there, refraction takes place at the first lens and the image is formed at I1. But we know that the second lens is also there. Refraction takes place at the second lens. For that we need an object. Therefore here I1 is the virtual object for the second lens. See here, this is the incoming ray. So it appears to come from I1. So I1 is the virtual object for the second lens whose final image is formed at I. Now let us apply the lens formula for both the lenses. For the lens A, what is the lens formula? 1 by f is 1 by v minus 1 by u. Or the focal length of the first length A is 1 by f1, and let us consider this distance to be some v1. Let this distance be u and let this distance be For the first lens, 1 by f1 is 1 by v1 minus 1 by u. For the second lens B, 1 by f2 is equal to 1 by v minus u, which means that for the second lens, this will be the object distance. So 1 by v minus 1 by v1. Let us add 1 and 2. We get 1 by f1 plus 1 by f2 is equal to 1 by v1 minus 1 by u plus 1 by v minus 1 by v1. So this will get cancelled. We get 1 by f1 plus 1 by f2 is equal to 1 by v minus 1 by u. Suppose we consider that the two lens can be considered to be a single lens of equivalent focal length f. U is the object distance and v is the image distance. Then for such an equivalent lens, we can write 1 by f equal to 1 by v minus 1 by u. So when we compare these two equations, the right hand side is the same. Therefore, 1 by f is equal to 1 by f1 plus 1 by f2. So whenever we combine lenses, the reciprocal of the focal length will be equal to the sum of the reciprocal of the individual focal length. So if you use more than two lenses, again any number of lenses we use, 1 by f will be 1 by f1 plus 1 by f2 plus 1 by f3 plus etc. We also know that 1 by f is power. So power will be the sum of the individual powers of the individual lenses. P is equal to P1 plus P2 plus P3, where P1, P2, P3 will be the individual powers of individual lenses. Now suppose one lens is positive and one lens is negative. We can write 1 by f will be equal to, suppose f1 is a convex lens and f2 is a concave lens. We write 1 by f is 1 by f1 minus 1 by f2, or f is equal to f1 f2 by f2 minus f1. Now in this combination, suppose if I say the focal length of both the lenses are the same. If f1 equal to f2, here the denominator becomes a 0. 1 by 0 is infinity, which means that the focal length tends to infinity, which means that the combination will behave as a glass plate. Suppose f1 is greater than f2. In that case, the denominator is negative, or the combination will behave as a concave lens. If f2 is greater than f1, the denominator is positive, therefore the combination will behave as a convex lens. Now like this you can use any number of lens and we can combine and we can get the desired focal length and magnification. Now since the image formed by the first lens acts as an object for the second lens, the magnification, the total magnification becomes the product of the individual magnification. That is M1 into M2 into M3 etc. If we are using two lenses, the total magnification will be M1 into M2. So like that the magnification is also increased.